In section 7.8, I'm going to go over how to use quadratic functions to model some real-life situations. In this first example, a toy rocket is launched upward, and its height above ground in feet after t seconds is given by this function. H of t equals negative 16 t squared plus 130 times t. Now sometimes you'll need to do some kind of a regression on your calculator to get this function. You know, in this case it would be a quadratic regression based on a set of data. So if you were given a problem that just had a table of data, you would make a scatter plot and then depending on the shape do some kind of a regression to get your function. And I went over that in the last section. So let's assume that we're starting with this function, and this is a quadratic function because the t is squared here. Now first I'd like to find h of 3 and interpret its meaning. Now the number in parentheses, this 3, is a time value, so that means 3 seconds have gone by, and we're trying to find the height at 3 seconds. So we just substitute a 3 in for time in our equation. So it would be negative 16 times 3 squared plus 130 times 3. And that comes out to be 246, and that would be in feet. So that means that after 3 seconds, the rocket is 246 feet high. So after 3 seconds, the rocket is 246 feet above ground. Now next I'd like to determine the times when the rocket is 100 feet above ground. So in this case, the height is being given to be 100 feet. So that would be substituted in for height on the left side of this equation. So we'd set that up by saying that 100 equals negative 16 t squared plus 130 t. Now this leads us to a quadratic equation. So we'd have to first subtract the 100 from both sides so we can get a 0 on one side of the equation. And then once we've done that, usually our strategy for solving a quadratic equation is to try to first try to factor this trinomial that's on the right side of the equation. But in this case it doesn't factor, so then we'll just use the quadratic formula to solve that. So we would have t equals negative b, so that'd be negative 130 plus or minus the square root of b squared, so that's 130 squared, minus 4 times a, which is negative 16, times c, which is negative 100, and that whole thing is divided by 2 times a, so 2 times negative 16. So now we just have to try to simplify this down. And so we have negative 130 plus or minus the square root of, okay, so I'm going to figure out what we have under the square root on my calculator. So it's 130 squared minus 4 times negative 16 times negative 100. And that comes out to be 10,500. And that's going to, the whole thing divided by negative 32. So in a situation like this, where it's an application, we really would like to get decimal answers for this. So first, I'll put this into my calculator using the plus sign. Okay, so I'll take negative 130 and add the square root of 10,500. And I'm going to hit enter to get that answer. And then divide that by negative 32. And that comes out to be about 0.86. So I'll write that solution down up here. So t equals 0.86 seconds. T equals 0.86 seconds. And then I'm going to do the same thing using the minus. So I'll take negative 130 minus the square root of 10,500. Hit enter. And then divide that by negative 32. And that comes out to be 7, if I round it off, 7.26. So t equals 7.26 seconds. So there's two solutions. There's two different times when it reaches 100 feet. What happens is that on the way up, it reaches 100 feet, and then it keeps going up to some maximum height, and then on the way back down, it reaches 100 feet again. So the reason we're getting two answers is because it reaches 100 feet on the way up, and then again on the way back down. Now you can also solve this graphically, and I'd like to show you on the graphing calculator how you can do that. And you'd start by pressing your y equals key and entering in your function. So you'd put in negative 16 x squared plus 130 x. And then you need to set up your window by pressing the window key. I'll make the x min 0 and the x max 10, so that'll go from 0 to 10 seconds. And then I'll change the y max to 300 because the rocket might go kind of high, so I want to make sure I can see it all. And I'll change the y scale to 10 and then hit graph. And you can see there's the graph of the quadratic function. That's a parabola. You can see it goes up and then comes back down. And then if I go into y equals and I put in the height of 100, which I'm trying to find when the rocket reaches 100 feet high, it'll put a horizontal line in at 100. And I'm looking for the points of intersection between the original curve. So we do second trace, and then down to intersect. And then for first curve, we'll just hit enter. And second curve, just hit enter again. And for the guess, you need to move your cursor over closer to one of the points. Let's find this one on the left first. And then hit enter again. And it will display right down here. You can see it says 0.86. And that's the same thing we got when we used the quadratic formula. And then I'll do this again. So second trace. So second and then trace. And then intersect. And then first curve, you just hit enter. And second curve, just hit enter again. And then for a guess, move it over closer to this other side. And then hit enter. And then it gives us the solution 7.26 seconds. And that is also the same that we got when we used the quadratic formula. So you can see you can get the answers to that problem algebraically by using the quadratic formula, but you can also get them graphically by putting in a horizontal line here at 100 feet high and finding the points of intersection between that horizontal line and the original function. Now next I'd like to try to find the maximum height of the rocket and the time when it reaches this height. So we're really looking for, this peak in the graph here. Now that's the vertex of a parabola, and we've learned previously how to find the vertex of a parabola. We would take negative b over 2a is the formula to find the x-coordinate, or the t-coordinate in this case. So t would be negative b over 2a. And b is 130, so it would be negative 130 divided by 2 times negative 16. So that's negative 130 divided by negative 32, and that comes out to be, if I round off, 4.06 seconds. So that's the time it takes to reach the maximum height, because that's the x-coordinate or t-coordinate of the vertex. Now to find out what the height is at that time, we'll just plug 4.06 in for t in our original function. So we'll just take h of 4.06, which would be negative 16 times 4.06 squared plus 130 times 4.06. And when I put that in my calculator, it comes out to be just about 264 feet high. So that would be your maximum height. So again, anytime you're trying to find the maximum, or it might be a minimum in a different problem, of a quadratic function or a parabola, you're really looking for the vertex. And to find that vertex, we're always going to use this formula, t, or in general x, equals negative b over 2a to get the x-coordinate. And then once we have the x-coordinate, we substitute that into the original function to find the y-coordinate. Now we can also find this maximum using our graphing calculator as well. So to do that, we'll do second and then trace. And then it's this command right here, maximum. And we'll hit enter on that. And then for a left bound, we have to use our left or right arrow keys to move the cursor a little to the left of where the maximum is, and then hit enter. And then it asks for a right bound, so move it to the right, and then hit enter again. And then it asks for a guess, so move it pretty close to where the maximum is, and hit enter again. And you'll see it shows you that the x value is 4.06. That's the same answer we got when we did it with our formula. And then the y value is 264, which again is the same answer we got down here. So we can also find this maximum height either algebraically, using the formula negative b over 2a to get the vertex, or we can do it graphically. Okay, now let's look at the question, when will the rocket hit the ground? Now, if it hits the ground, that means the height is 0. So that's what you have to realize. So hitting the ground means the height is 0. So h of t, which represents the height, would be 0. So we'll substitute a 0 in for h of t over here on the left side of our equation. So we'd have 0 equals negative 16 t squared plus 130 t. And this equation is really easy to solve because, first of all, you can just pull a common factor of t out of both terms. Now there's probably common factors in these numbers too, but you don't really need to pull those out. All you really need to do is pull the common factor of t out. So that gives you 0 equals t times negative 16t plus 130. And then you can set each part equal to 0. So t equals 0, and then negative 16t plus 130 equals 0. And this would give you negative 16t equals negative 130. And then when you divide both sides by negative 16, you get 8.125 seconds. And that would tell you really when it's going to come back and hit the ground. This solution here is showing you that it starts out on the ground, but then after it goes up and then comes back down, it's going to hit the ground after 8.125 seconds. Okay, this problem can also be solved on our calculator. What we're really finding here is an x-intercept. We're finding where the graph crosses the x-axis right here. And, you know, it crosses over here too, but we're really interested in this point when it hits the ground. So that's an x-intercept. And on your calculator, the way you can find an x-intercept is by first pressing second and then second and then trace, and then go to the 0 command. And then for left bound, you want to move your cursor so it's a little to the left of the x-intercept. And for right bound, move it a little to the right. You'll know it's to the right when the height shows up as a negative number here. And then for a guess, just move it as close as you can to that point. And then hit enter. And notice it gives you the answer. It says x equals 8.125, which is the exact same answer we got here. And notice it's showing you that the y coordinate is 0 at that point. Now in this next example, I'm going to show you that you can actually use a system of equations that involve quadratic models to solve some problems. A system of equations means you have more than one equation. So in this case, we have some data given to us on the median age at which both women and men get married for the first time. And you can see the data for the women is given in this first column, and for men in that last one there. So we want to, first of all, in part A, find a regression equation of women's median marrying age and another regression equation for men's median marrying age. So we want to find two different regression models, one for women and one for men. And we're assuming that T is the number of years since 1900. So since T is the number of years since 1900, T would really be 40, and then 50, and then 60, 70, 80, 90, and 100. And so to do a regression equation for women, let's start with that. We would go in our calculator and we'd put the T into L1 and women's ages at which they get married into L2. And then we could make a scatter plot of that, and based on the picture, decide what kind of regression might work and get a regression model for women. So I've put this data into my calculator with the time in L1 and the women's ages in L2. And now we're going to do a regression. So we'll use the calculator. We'll do, first I'll just make sure my stat plot is turned on, and we'll do zoom 9 to get a picture of the scatter plot. And you can see that does seem to follow a quadratic function like a parabola. So we'll do stat and calculate, and we'll go down here to quadratic regression, and we'll hit enter. Now I'd actually like to have my calculator store the answers into Y1. So I'll hit this vars key and then go to yvars and then function and then Y1. And that'll store the answer in Y1 so I could easily graph it. And then I'll hit enter. And here's the equation. I'll write that down in a minute. And now let's go ahead and graph it so we can see the picture. And you can see that model does fit the points very well. Okay, so now we have to do the same thing for the men's data. So as you can see, I've put the men's ages into L3, and I would like to make my calculator add that scatter plot in and keep the other one. So the way we can do that is by using statplot2 for the men's data. So let's start by pressing second and then y equals, and then we'll go to the statplot2 and we'll hit enter and we'll turn it on, and we have to change this L2 to an L3, which we do by doing second and then the number 3, and that's where the men's ages are. And then we'll just hit the graph key, and you can see it's still got the women's data in there, but in here is the men's points up here. So now to get a regression for the men's data, we're going to hit stat, and then we'll go to calculate, and then we'll go down to quadratic regression. And now this time, since we're doing L1 versus L3, we have to indicate that. So we'll do second 1 for L1, and then a comma, and then second and then 3 for L3, and then a comma. And then I'm going to store the answer into y2. So I do vars, and then y-vars, and then function. And this time I'll choose y2 because I already have the women's equation in y1. And here is our equation. I'll write that down in a minute. And I'll just go ahead and graph that. And it should show us both models together. So you can see we've got two quadratic models, and we'd like to, notice in part B, predict when the median age or ages at which women and men first marry will be equal. So when they equal, we're really looking for where these graphs will cross, and we can find that point of intersection graphically, but we can also find this answer algebraically using the quadratic regression models that we got. And so I'd like to show you how we can do that both ways. Now I've written down both of the regression models for both the women and the men right here. Okay, and these are the ones that we got from our calculator from doing those two quadratic regressions that I just got done with. So now if we want to find when those ages will be equal, since they're both equal to y, we can just set the two equations equal to one another. Okay, so I've set that up. I've just taken this entire equation and put it on the left side of the equation, and then taken this entire model for the men and put that on the right side of the equation. I couldn't quite fit it, so I had to go down to another line there. Okay, so we basically have the women's model equaling the men's model. And to solve that, we want to get a 0 on one side. So we want to collect all the terms to the same side of the equation. And then we'll just go ahead and use the quadratic formula. So when I collected all the terms to the left side of the equation, this is the result that I have, and this is now in standard form. So I can use the quadratic formula to solve for t. So t would be negative b, which is actually positive 0.022, plus or minus the square root of b squared, so negative 0.022 as a quantity squared, minus 4 times a, which is 0.00025, times c, which is negative 2.19, and the whole thing is divided by 2 times a, so 2 times 0.00025. And that would give us t equals 0.022 plus or minus the square root of 0.002674 divided by 0.0005. Now we'll change, we'll convert these over to decimals by working them out on the calculator. First I'll use the plus, and when I do that calculation using the plus, the answer comes out to be 147.4. And when you use the minus, you actually get a negative solution, which would mean you're going backwards in time from where this problem started. And I don't think we should do that. So we're just trying to project into the future here. Where are these two curves going to come together and meet? And so the answer, according to the quadratic formula, it would happen in 147 years. And remember, time in this problem is all measured from the year 1900. So if you take 1900 and add 147.4 to it, you actually come out with the year 2047. During that year, it actually is 2047.4. So that would be our projection. Now we can check this on our calculator as well if we find a point of intersection between these two graphs. So first I'll just change my window so that I can actually see these graphs intersect. So if I go to the window key, we need to see further to the right and further up. So I'll change my X max to a bigger number. I'll try 150. And I'll change the Y max to a bigger number. I'll try 50. And then I'll regraph it. And hopefully I can see these two models cross somewhere in the future. And it does look like they cross right about here. So we can do second and then trace and then intersect to find where they cross exactly. And first curve, just hit enter, and second curve, enter, and guess. You can slide it up close and then hit enter. And the calculator will then find that point of intersection. And you can see it happens at, the calculator says 146.7. So that would round off to about 147 years, which is pretty close to the answer we got. I'm guessing the small difference in the answers is due to the fact that I've rounded these decimals off in these models. So when I wrote down these quadratic models at the beginning, I did some rounding. And so that would explain for that small difference. But for more or less, it checks out. Both answers come out to be about 147 years. The last example I'd like to go over deals with revenue and trying to maximize revenue. Okay, and in this problem, it tells you that a ski club charters a bus that normally costs $250 per person, but a group discount reduces the fare by $5 for each ticket sold. The more tickets sold, the lower is the per person fare. And it says there are 31 seats on the bus, including 1 seat for the driver. What size of the group would maximize the company's revenue? Okay, so the key thing is here that we're trying to maximize the company's revenue. And before we can maximize the revenue, we have to come up with an equation for the revenue. And part of that is going to involve representing the price. So in this case, the price, we'll call that P of X, is going to be $250 because that's how much it costs per person, then minus $5 for every ticket sold. And I'm going to let X be the number of tickets sold. So it's going to cost $250 per person minus 5 times however many tickets are sold. So there's a discount there. Now once we get that, the revenue, which is the total amount of money that comes into a business, you take the number you sell times the price for each. And if you multiply them together, that gives you your total revenue. So the number sold is X. So that's the number of tickets sold. And the price for each is P of X. So the formula for revenue, it's just X times P of X. So in this case, it would be X times 250 minus 5X. Which if you multiply that out, the revenue, I'm going to call that R of X for the revenue, would be negative 5X squared, I'll put that one first, plus 250X. Now that is a quadratic function. And not only is it a quadratic function, the graph would be a parabola, as all quadratic functions are. And since the leading coefficient is negative, it's a negative 5, the parabola would open downward, so the graph would look something like this. And there's going to be some high point there. And that's what we're trying to find. We're trying to maximize the revenue, which is it's going to be the vertex of that parabola. Now we've learned that the vertex will be located at the point x equals negative b over 2a, which in this case would be negative 250 over 2 times negative 5 which is negative 10, and that comes out to be 25. Now that's the number of tickets that would need to be sold to maximize this company's revenue. And to actually find out what the maximum revenue is, you would calculate the revenue obtained by selling 25 tickets by plugging a 25 into your original function. So it would be negative 5 times 25 squared plus 250 times 25. And when you work that out, it comes out to be $3,125. And that amount of money right there would be the maximum revenue. So finding the maximum revenue involves first finding an equation for the price, then multiplying that by x to get an equation for the revenue, which is usually going to come out to be a quadratic function. And then we can use our vertex formula to find where that maximum occurs.